In this lesson, we will learn about Pascal's triangle, which was discovered by several mathematicians before Pascal, but became famously associated with his name. Since it was discovered by different scientists in various locations, this indicates that it describes many natural phenomena. Let's try to understand the triangle which is right in front of us right now. We notice that it always starts with the number 1 on both sides, meaning the edges are always equal to 1. We also observe that each row increases by one element compared to the previous one. This is why when we extend the rows we get a triangle shape, hence the name. If we look at each row, we notice that it always starts with the number 1, then rises at a certain rate until it reaches a peak, and then decreases at the same rate until it returns to the number 1 again. Perhaps this is the exact behavior that links it to so many natural phenomena. And we can also observe symmetry between the right and left sides of the triangle. Let's take a look at the 7th row of the triangle. We observe symmetry between the right and left sides around the central element. This symmetry helps us understand each row of Pascal's triangle and help us construct the triangle as well. So how can we construct Pascal's triangle? If we notice, each number is the sum of the number above it and the number to the left of that number. For instance, the 4 here is the sum of 3 and 1, and the 6 here is the sum of 3 and 3, and the 10 here is the sum of 6 and 4, and so on. So understanding this pattern, in addition to the point we have mentioned that each row of Pascal's triangle has n plus 1 terms, this way we can derive infinitely many rows of Pascal's triangle. Now let's take a very important example of mathematical operations that Pascal's triangle can simplify: the binomial theorem. We use the binomial theorem to expand the brackets of this form: two numbers added together between brackets raised to the power n. So if n is equal to 0, the result will be 1, and if n is equal to 1, the result will be a plus b, and if n is equal to 2, expanding the square give us a squared plus 2ab plus b squared. If we continue expanding for n is equal to 3, 4, 5, the process becomes a bit lengthy. So how can we use Pascal's triangle to simplify this process? If we look at the coefficients of each term, we notice that they match exactly with Pascal's triangle. For example, at the start we have 1, and in Pascal's triangle the first row is also 1. Then we have 1, 1, which matches the second row of Pascal's triangle. Then we have 1, 2, 1, and so on. This means we can use Pascal's triangle to expand binomials without relying on the binomial theorem, which may require lengthy calculations sometimes. And finally, it's very important to notice that we only deduce the coefficients of the expanded terms from Pascal's triangle.